All right, organickers, now is the time, the unfortunate time, when we have to start doing some memorizing. One of the things that you'll find about organic chemistry is it's pretty important to kind of learn the language and become a little bit conversant. And really the only way to do that is to just consistently look at these things, which is why I really recommend note cards. And so we're going to go through not every single functional group that we could talk about, but kind of the ones that are going to be most important at the beginning here. Obviously, that's what this whole entire class is all about. By the time we get to Chem 243, we'll have a list of probably 20 functional groups that we know everything there is to know about their physical and chemical properties and what they react with, what their modes of the mechanistic modes of action are and stuff like that. But now we just kind of got to learn them. It's kind of painful. It feels like a biology class, but don't tell anybody I said that, where we just kind of have to memorize things and ways of doing things. We're also along the way going to learn this concept of condensed structures, which is kind of where we take all those pretty three-dimensional pictures that we've been showing and condense them down into just a single line of confusingness, right? And so each functional group, well, not each one, but most functional groups kind of have a really specific way of being represented in condensed structures. That's where we're headed. So hold the phone. The most simple group is called the Alkane group, which we've already talked about. As I said, if you're talking about alkanes, you are not talking about anything exciting. You're just talking about something you're probably going to burn or try really hard to turn into something much more interesting. So here are just kind of two alkanes. This is our old friend ethane, and whatever the heck this thing is, I guess it would be 2,2-dimethyl-butane, I think. Yeah, that's it. But as I said, we'll learn how to name in a future video. One thing I wanted to show you, by the way, I might as well label these things, is alkanes. Not really technically a functional group. It's just the simplest hydrocarbon that kind of everything else is based on. These guys are all considered saturated hydrocarbons. When you see that word saturated, that just means it has as many possible H's connected to it as possible, right? Double bonds aren't allowed, triple bonds aren't allowed. Well, I guess technically rings would be allowed, but really specific kinds. But anyway, these are all called saturated hydrocarbons, and they're really boring to write. So let's not have to worry about all these different hydrogens and carbons and showing them. Let's kind of learn this thing called a skeletal structure, first of all. And this is not a condensed structure, it's a skeletal structure. What we would do in this particular case is we'd show a squiggle for the longest carbon chain. There's my longest carbon chain. And we'd kind of stick two other methyl groups off of there like that. And so it turns out one of the kind of mind screws starting off in organic chemistry is that I put something like that on the board, which looks like a pretty balloon animal, right? But it actually means quite a bit, right? It tells you that each one of these ends has a carbon, each little bend has a carbon, and it's your job to remember that there's actually hydrogens in there. And that's going to lead to when we get mostly into like the end of first term and in second term, is a lot of times those hydrogens become important. So it's a way that I can trick you because I'm very tricky. I could hide the hydrogens by writing it like this, and you kind of have to know they're in there. Well, it turns out in terms of drawing, the skeletal structures, they're pretty easy, but there's a way that you can kind of write this out as what's called a condensed structure. This one's pretty boring, right? A condensed structure there is just going to be, let's draw it in red, hopefully you guys can still see that. Condensed structure for this thing, whoa, 2 CH3s. This particular guy though, you'll notice that we can kind of group things together and write this as a line. So what I'm going to do is draw that thing out like that. And you'll notice that the like groups, I combine together in this little parentheses looking thing. And then of course we've got that ethyl group kind of hanging off the end there. And so what you can do is, as you get better and better at organic chemistry, you can see this, that'll pop into your head, and even maybe more detail, right, with three-dimensional bonds and stuff like that. Even better, right, you can look at that and think of it as this. Or you kind of look at that and you say, oh, okay, well, I could also represent that as this. So the very first homework is going to have you guys kind of practicing a little bit with these types of condensed structures. Let's go on to the next group. And we'll show how to do condensed structures for those. The first exciting group that we'll talk about, functional group, is called the alkene functional group. That's what the end of first term is going to be all about, understanding the reactions of. Turns out that just the simple act of putting a double bond between carbons makes that thing much more reactive, right? Carbon-carbon bonds and carbon-hydrogen bonds, pretty boring to react with. But that second bond in here is so much weaker, it's very easy to get it to, I shouldn't say the second of these bonds, right? The pi bond that we'll talk about very soon is a much weaker overlap. It results from the sideways overlap of p orbitals, which you probably talked about in Gen Chem. We'll get there, don't worry about it. But anyway, how do you draw that thing in condensed structures? Well, first of all, this is the alkene functional group. Anything in organic chemistry's got kind of like old-timey ways of referring to things, which you'll pick up on over time. The old-timey way of referring to alkenes is actually olefins. Don't worry about that one. Nobody uses it except for old people like me anymore. But alkenes, if we're going to do a condensed structure for this sucker, it's pretty straightforward. You would just draw something like that. You might, so if you were going to take this condensed structural formula and then try to make it into this formula, one of the things you'd notice is you connect all the carbons together, of course, but then you'd look at this thing and be like, well, that carbon doesn't see enough electron. Oh my God, I screwed this up. I'm sorry, everybody. I should probably edit this out, but I'm too lazy. There should be another H in there. Ugh. Remember carbon bonds 4 times? Who said that? I don't know. I should listen to that guy. So anyway, this guy is actually going to change. We'll stick an H in here. So anyway, when you drew this out correctly, you would have noticed that that carbon doesn't have enough bonds attached to it. So that's kind of your reminder that, oh, I must have another bond in there. Well, not too difficult. But that's the way we can do condensed structures for those guys. Sometimes you'll see like the actual double bond written in there, but it doesn't have to be. Okay, next group. These guys are called alkynes. And you'll notice that I just drew a skeletal structure. So you can certainly draw this out if you would like to. I'm just going to convert it directly to its condensed structural formula. Let's show a little bit of extra pizzazz in here. So I'm representing that CH3 there. I'm representing 2 CH2s with this little parentheses, right? So that's just kind of getting back to that the alkane way of doing things. And then this guy in the middle will be represented as a CC, and then that alpha group at the end. All right, so not too interesting. Alkynes, that triple bond is indicated by kind of 2 C's being right next to one another. Okay, so the first non-carbon containing functional group that we're going to talk about is this thing, which we've kind of seen before in a different video. This thing is called an alcohol. We'll actually eventually start to call this thing a secondary alcohol. And so the condensed way of doing these guys quite often would be something to this effect. You'd show CH3, CH with an OH in parentheses, followed by the end of that group. Right? Usually, if there's an alcohol in the middle of something, it will in fact be shown in parentheses. You don't always see that if the alcohol is on the end of the thing. But that's definitely one group that's important to know about. And yeah, that's all I have to say about that. All right, so we have what kind of looks like the beginning of an alcohol, but instead of having another hydrogen connected, we've got another carbon group. This is something called an ether. And it turns out the condensed structure way of doing ethers is super straightforward. I'm going to group these two ethyl groups together and just put an oxygen there. So pretty much no change, right? Pretty easy to see. I could have put this group and oxygen and another group on the other side, but you pretty much just use an O, right? No parentheses, no weird ways of doing things. We're going to go on to talking about a group called the kind of carbonyl-based functional groups, and things are going to get a little bit more interesting. I'm going to probably put all of the carbonyl-containing functional groups on here, and we'll just kind of do them all together so we can get through this craziness. Okay, so first thing we got to talk about with this particular set is what a carbonyl is. Carbonyl is itself not a functional group, it's just a method of bonding for carbon. Anytime you hear me mention the word carbonyl, what I'm talking about is this carbon and oxygen bond right here. That is called a carbonyl. And it turns out that there's a whole bunch of different groups, all with completely different reactivities and physical properties that are all based upon this carbonyl group. Of course, there's a zillion of them. These are the most important at this point in your education. So this guy is called a carboxylic acid. Oh, incidentally, make sure you look at the resource guide for today. I have kind of a simplified list of a bunch of different functional groups that we're going to see in the first couple of weeks that we should start to memorize. These are kind of those, like the most important in my opinion. Okay, so this guy right here, this is a carboxylic acid. Obviously, it's called that because it is the acid in organic chemistry. It's the most common acid. The way that we can represent this thing as an abbreviated structure makes it look like coo. Not cool, coo. So this guy is a condensed structure, which hopefully you can even read, is going to look like that, right? It turns out that listing off the oxygens in that particular manner tells you automatically that you're talking about a carboxylic acid. This is where those condensed structures start to get a little bit funky because the way that we put things together tells you a little bit about the three-dimensional, or I should say two-dimensional, I guess, structure of this thing. So that's just kind of something to memorize. This guy down here is called a Carboxylic Ester, or just an ester for short, not to be confused with the ether that we just saw. This is an ester. And the way that you can tell it's an ester is that we have a carbonyl carbon, an oxygen on one side, some sort of carbon-containing group on the other, and then that oxygen is itself bonded to another type of carbon chain. The difference between an ester and a carboxylic acid was the presence of that H, right? That acidic H makes it a carboxylic acid. If there is no acidic H, this thing is then called an ester. And this thing written out, as you probably are not going to be surprised by, looks like a coo. With the rest of those carbon-containing groups written out there. This guy, this is called an amide group. Not to be confused with the other amide, which is that minus charged nitrogen thing. Weirdly, we call minus charged nitrogens the same thing as we call the organic functional group. I don't know why it is. Don't ask me. It's probably the Germans' fault. It usually is. So this guy is called an amide. And so typically with these guys, what you would see is you would see the normal way of doing things would be to do something kind of like this. And I will say that quite often that oxygen, just to not confuse people to think that, oh, there's a carbon with an oxygen directly bonded to a nitrogen, quite often, not all the time, but quite often there'll be a parentheses in here. So usually parentheses, when you see them in condensed formulas, is showing you that there's something kind of hanging off of the chain. It's not in the middle of the carbon chain. And of course, we could also draw, if there was another methyl group down here, we could draw parentheses with a 2 down there. Not too bad. So to recognize an amide, obviously, I don't mean to insult your intelligence here, but you've got some sort of carbonyl carbon, a nitrogen on one side, a carbon on the other. Turns out that you can have what's called primary amides, which only have 2 hydrogens attached. This is considered a secondary amide. There's also tertiary. We'll talk about all that stuff. The last 2 groups that I want to get to are these guys. And this guy is called a ketone. This, which we've seen before in a previous video, is called an aldehyde. The way that we're going to show these guys is going to be pretty similar to what we saw down here with that little parentheses mark there. We are going to show this thing, I'll just write it up here, as a CH3, COCH3. You'll notice that when it's written like this, you might think like, oh, that must be an ether with a whole bunch of bonds. No, it's really not, right? That's not actually a very stable molecule. So at least at the start here, I want to show you that it often will look like this, but when you actually draw your homework and you're using it to study and stuff like that, you can never hurt to put parentheses in there so that you kind of know, it's kind of a clue to you that that oxygen is actually kind of hanging off of the chain. The aldehyde is one thing we got to be really careful about, because this guy, when we draw it out as a condensed structure, is going to look like CHO, right? If you see CHO anywhere, that is 100% an aldehyde. And what confuses students quite often is they'll put OH down, right? But OH is always an alcohol. So you have to remember that the aldehyde, right, has to be represented like this. Otherwise, you often confuse it with an alcohol and things like that. We could go on for like another 2 hours with this if you want to, but I'm not going to subject you to that. I'll probably torture you with some other sort of video. So we'll call it right here. As I said, really great idea to make note cards for all of these folks. See you soon.